So in this video, we're going to talk a little bit how energy relates to kind of physical and chemical changes and how it affects the system versus the surroundings. Physical and chemical changes are usually associated with a change in energy as well. So like if you're thinking about it, for example, when water evaporates from your skin on a hot day, that's going to be a physical change. So the water molecules take some of the thermal energy from your body, so it takes some of that energy away, so that they can go through the physical change of going from a liquid to a gas. So there was an exchange of energy there. The water took the thermal energy to complete the phase change, and your skin gave up the thermal energy, and then you felt cooler, therefore. And then, for example, when you light a lighter, it's a chemical change. We've talked about that. So when you're burning the gas, you're transforming the molecules from butane and oxygen to carbon dioxide and water. And in this case, energy is released into the environment so that we can use it. So when we're talking about kind of kinetic energy and potential energy equal total energy, it's kind of the total energy in the system and the surroundings. So we're going to start to compare how we can move energy between the system and the surroundings, but our total energy of everything together is going to stay the same. So we can think about how energy is associated with chemical reactions and chemical molecules more specifically. So remember, systems high in potential energy want to convert that energy to kinetic energy to lower the amount of potential energy in the system. Again, remember that total energy stays the same. So it might give up some energy to the surroundings, it might take on some energy from the surroundings. But if we look at our system and the surroundings, the total amount of energy we have stays the same, and maybe we're just going to exchange some energy between the two. So when I say system, let me be a little bit more clear to say I mean like the molecules involved in our chemical reaction, and everything outside of that would be the surroundings. Or if we're thinking about, heating a solid and turning it into a liquid, the system therefore is the brick of solid itself, and then the surroundings again are just everything around it. So it's actually the system is like the molecules we're studying in question here, and the surroundings are going to be everything else. So this exchange of kinetic and potential energy drives a lot of chemical reactions. So if a bunch of molecules can use a little bit of starting energy to rearrange their particles into a lower potential energy state, boom, they absolutely will. They're like, yeah, let's do it. This is what I need. So that can, again, drives certain kinds of chemical reactions and drives like a lot of the spontaneous things that happen in our lives. Some chemicals have a lot of potential energy stored in their chemical bonds. This is, again, of course, chemical energy, like TNT, the explosive, for example. Why it's so explosive is it only takes a teeny tiny spark of energy, right? We think about like like Wile E. Coyote, lighting just the fuse that runs across, right? That, eventually blows up the dynamite TNT, right? So it just takes that little spark from that fuse. So that fuse burning, giving off those sparks is what starts this gigantic chain reaction. Well, if we put just a tiny bit of energy into those chemical molecules, it's just enough to get everything kind of kick-started so that we can move from a really high potential energy state to a lower potential energy state. So there's a ton of potential energy in TNT based upon how the chemical bonds are arranged and the type of bonds that they are. So when that energy is being released, it's a lot of energy coming back out when it's moving to that lower potential energy state. For example, also, some chemicals don't have as much potential energy stored in their bonds, so they're much more stable. You'd have to put in a ton of energy for them to change, right? So water stays as water all the time. It takes a lot of energy to decompose it into its two parts of hydrogen and oxygen. So that's a more stable molecule. There's not as much potential energy stored in that kind of chemical bond. And so, as I mentioned before, we're going to talk about energy exchange between system and surroundings, remembering that system's going to be whatever chemical molecules are in question here. Surroundings are going to be everything around it. So it can be interesting to compare how that changes during a physical change or a chemical change. So it's interesting to think about how energy is exchanged between that system and the surroundings. So we have two different kinds of things that can happen there, right? We could have energy going from the system to the surroundings, or from the surroundings into the system. But again, the total energy of the two combined together still stays the same. So if we have it where the system is transferring energy out to the surroundings, we're going to call that an exothermic reaction. Okay, so an exothermic reaction means it goes from the system to the surroundings. So for example, that might be when we go from a liquid to a solid. So if we think about it, we got to take the heat out of there. We got to take the random motion of those molecules away from that liquid so that it can become a solid, so they stay more rigid. We're going to take energy out of the system. Like when you put water in the freezer, remember it gets colder, so we're going to take energy out of the system. And then, for example, where we go from a gas to a liquid, so it's getting colder, it's going to take energy, it's going to give energy off to its surroundings so that it can become a liquid from a gas. Combustion, for example, again, we know that's exothermic. We're going to give a ton of energy out in heat as you light a lighter, for example, or breathing is also an exothermic reaction. So we're giving energy off to our surroundings when we breathe. Energy. So you get more energy out of the system than you have to put in to start that process. So every system has to have that tiny spark, that kickstart to get going. However, in an exothermic reaction, the energy that it gives off is much more than that tiny spark that got it going. An endothermic process or an endothermic reaction is going to be the exact opposite. So it means that the system is going to take on energy from its surroundings. So therefore, it might be if we're going to make a solid to a liquid, remember we have to heat ice so that it becomes liquid water. So I'm putting energy in from my burner on the stove, for example, or if I'm boiling water, taking it from a liquid to a gas. In that case, again, if I've got my pan on the stove, I'm getting all of that energy from burning that fire, from that exothermic reaction, and I'm using that to boil my water, take it from a liquid to a gas. Another place where you might encounter an exothermic reaction is like in instant ice packs when you crack that and it feels cold. So if something feels cold when the reaction happens, it's going to be an endothermic reaction. And there's a couple more examples down here. So in an endothermic reaction, you have to keep putting energy in from the surroundings. It's going to keep taking from the surroundings more than what you're actually getting out from your transfer of potential to kinetic energy. So if a process is endothermic in one direction, it's going to be exothermic in the reverse process. So if we think about it, if a solid goes to liquid, it's endothermic because you need energy from the surroundings like a flame to melt the solid. However, when we go from a solid to a liquid, it's exothermic because we're giving energy up to our surroundings, like putting it in the freezer to make that liquid a solid. So we're just looking again at the exchange of energy between those two different systems. Slide here, we have a couple of visual representations of how we can look at the energy in an endothermic and exothermic reaction. So on our left-hand vertical axis on our top picture here, we can see we have stored chemical energy. Remember, that's going to be potential energy. So the direction of reaction means time as the reaction goes on. So we're thinking about the starting point to the ending point, reactants to products. So if we're going from reactants to products, then our energy, if we increase in energy, potential energy from our reactants to our products, then we have an endothermic process. So energy is absorbed by the system. So this is reactants and products. We're only looking at the system here. So energy is absorbed into the system from the surroundings. And then the representation on the right shows the exothermic reaction, where we're looking at energy being released from the reactants to the products to get there. So we're releasing energy to the environment, the surroundings, from the system to the surroundings to get from reactants to products in that case. And then we have another representation where we're looking at it in just terms of increasing energy. So increasing potential energy, if we have to increase in potential energy from reactants to products, we have an endothermic reaction. And if we increase in energy from products to reactants, then that means we've released energy. So we've gone down from the reactants to the products. We have an exothermic reaction. Okay, so let's quickly work through some examples of endothermic and exothermic processes or reactions. So if I have some potassium chloride, I take that solid, I mix it into water. The test tube feels cold in my hand. So if something feels cold, that means you have energy going into the system. It's taking energy from the surroundings into the system, so the test tube feels cold to the touch in your hand. So if it's going from your hand to the test tube, that means, or the reaction in the test tube, that means that you have an endothermic process from the surroundings into the system. When we're thinking about when water like condenses onto a surface, it's going from a gas to a liquid. So going from a gas to a liquid, we're kind of taking away some of that random motionability of the particles. So we're decreasing that thermal energy. So if we're going to decrease the thermal energy in our molecules in the system, that means we're going to give that energy up to the surroundings. So if we're going from the system to the surroundings, we have an exothermic process. If you put bread in the oven to bake it, right? So we've got a chemical reaction that happens when we put our bread into the oven to bake it. So when that happens, we're going to take the room temperature bread, we're going to put it in the our bread dough, we're going to put it in the oven, and then when it's baking, it's taking the heat from the oven and using that to make the chemical processes happen. So if it's going from the surroundings, the oven, into that chemical system, from the surroundings into the system, that means we have an endothermic process. So just because it's really, really hot in the oven doesn't mean that baking bread isn't an endothermic process. So what I don't want you to do is associate endothermic with cold and exothermic with hot, because that's not necessarily true. It's all about the relationship of the process when the energy is moving between the system and the surroundings. And then our last example here, so if calcium oxide is mixed into water, that means that and when it's mixed into water, the test tube feels warm to the touch in your hand. You can feel the energy coming off of the reaction. You can feel that heat energy in your hand. So that means there's energy coming out of the system into the surroundings, aka your hand. So it's going to be an exothermic process. So those are some examples there for you to work through and think about. So that's a little bit how energy changes and moves within systems when we have physical and chemical changes.